Good morning, friends. Up to this, we discussed about what are the MCQ question asked in Neet exam. Up to the 2010, we discussed it. Now today, we discuss the more question also asked in Neet and All India PMT exam. Now, the question asked in 2010, a source S1 produce 10⁻15 photons per second, having wavelength of 5000 angstrom. Another source S2 also produces 1.02 into 10⁻15 photons per second, having wavelength also the same wavelength 5000 angstrom. So for these two sources, we have to find out the ratio of power P2 upon P1. That means we have to find out the ratio of power of second source to the source 1. Now friends, we know that the energy radiated per unit time, that is known as the power. And energy, we know that there is the NHF. Therefore, the energy of source S1 per second is energy per second for source S1 is P1 is equal to N1 Hc upon lambda 1. That is our equation 1. And for source S2 and for second source S2, power P2 is equal to N2 Hc upon lambda 2. From these two equations, we take the ratio P2 upon P1. P2 upon P1 is equal to N2 upon N1 into lambda 1 upon lambda 2. Because here the power is inversely proportional to the wavelength and directly proportional to the number of photons. We take the ratio P2 upon P1. Therefore, N2 upon N1 into lambda 1 upon lambda 2. Lambda 1 and lambda 2 are same. So, is equal to only N2 upon N1. That is cancelled. Because the both are same. 5000 angstrom, 5000 angstrom. We substitute the value 1.02 into 10⁻15 upon 10⁻15. So 10⁻15 cancel. So ratio of the power of these two sources is 1.02. That is 1.02. Clear it? That is our answer. Again, here the two sources given S1 and S2. Both emits the photon per second are given respectively 10⁻15 and second source 1.02 into 10⁻15. Wavelength of emitted photons in both cases are same, that is the 5000 angstrom. So, what should be the ratio of the power of source S2 to the source S1? Power is the energy per unit time. Here, the energy radiated by the source S1 is, we know that E is equal to NHF and E is equal to NHF, NHc upon lambda in terms of the wavelength. Therefore, the energy radiated per second power is equal to N1 Hc upon lambda 1. That is for source S1. And for source S2, P2 is N2 Hc upon lambda 2. Taking the ratio of equation 2 to 1, P2 upon P1 is equal to N2 upon N1 into lambda 1 upon lambda 2. Here, lambda 1 and lambda 2 are given equal. Both are 5000 angstrom. Therefore, we can cancel it. Therefore, the ratio of the power is equal to the ratio of number of photons emitted per second. So, this way we obtain the answer is 1.02. Clear it? Okay. After that, the next question also asked in 2010. Ultraviolet light of 200 nanometer wavelength is incident on nickel having wire function is 5.01 electron volt. Potential difference of blank volt should be applied to stop the electron emitted with maximum speed. So here the nickel metal is given having the work function is 5.01 electron volt. On this nickel metal, the radiation of or the ultraviolet light of 200 nanometer is incident. So as a result, the photoelectrons are emitted with the maximum kinetic energy. To stop this photoelectron, how much potential difference we should apply? For that purpose, we know that the maximum kinetic energy is equal to HF minus phi, right? So applying this equation, maximum kinetic energy K maximum is equal to Hc upon lambda minus phi. Work function. Work function is already given, and we also know that there is the EV0 or the EV. Now we substitute the value. Therefore, H 6.62 into 10⁻² minus 34. C, velocity of light 3 into 10⁸ in denominator lambda in electron volt. Now, this term is in joule. We have to convert into electron volt. Therefore, divided by 1.6 into 10⁻² minus 19. Lambda as it is, lambda in angstrom minus 5.01 electron volt. So the simplification of this part is already in earlier numerical we discussed is 1.2375 divided by lambda minus 5.01. Already in earlier numerical we simplified it. So there is the 12375 electron volt divided by lambda minus 5.01. So its simplification is 6.1875. 6.1875 minus 5.01 is equal to 1.177, approximate 1.2 volt. As we apply the potential difference of 1.2 volt. So no any photoelectron can reach to the collector after the emission with the maximum kinetic energy. Actually, this equation is of Einstein's equation. Maximum kinetic energy is equal to EV0 is equal to HF minus phi, and F is equal to C by lambda. Now again repeat it. That is asked in 2010. Here ultraviolet light of 200 nanometer is incident on a nickel metal having the work function of 5.01 electron volt. So what should be the potential difference applied to stop the electron emitted with the maximum speed? For that purpose, we know that the equation maximum kinetic energy is equal to EV0 is equal to HF minus phi. F is equal to C by lambda. So we can write K maximum is equal to Hc upon lambda minus phi. So here we substitute the value of H 6.62 into 10⁻² minus 34. Velocity of light 3 into 10⁸ upon 1.6 into 10⁻² minus 19 to convert the Hc into electron volt divided by lambda in angstrom minus 5.01 electron volt. Therefore, as we simplify, we obtain the answer is 1.2 volt. Now next, on the base of the theory, this question is asked on the base of Davison and Germer's experiment. In Davison-Germer experiment, in order to increase velocity of electron emitted from electron gun. So which of the following option is that? For that purpose, the first is given the potential difference between the anode and filament should be increased. Second option is filament current should be increased. Third is filament current should be decreased. Now next, fourth option, potential difference between the anode and filament should be decreased. Now listen here. What are the photoelectrons or the electron emitted from the electron gun? These electrons are accelerated by applying the high tension battery. What are the electrons emitted from the electron gun having the negative charge? We apply the positive potential on anode to increase its kinetic energy. Therefore, as we increase the potential difference between anode and filament, and this potential difference is positive, therefore the force of attraction acting on emitted electron is increases, therefore the speed of emitted electron also increases. And due to that reason, the option A is right. Potential difference between the anode and filament should be increased. So as a result, what are the electrons are emitted from the electron gun are attacked with the more speed. That means its velocity is increases. Its velocity must be increases. Clear it? Okay. Now after that, the next 34. In electron microscope, 25 kilovolt voltage is applied to accelerate electron. Now, by changing the voltage to 100 kilovolt, de Broglie wavelength becomes. Initially, in electron microscope, we are applying the 25 kilovolt potential difference. Now, we increase this voltage from 25 kilovolt to 100 kilovolt. So what should be the de Broglie wavelength of electron which are emitted? So we know that lambda is equal to de Broglie wavelength is equal to S upon P. P is equal to 2 MeV. Right? Here I write here the solution of question number 34. Lambda is equal to H upon under root of 2 MeV. H is the Planck's constant 2. Constant M, mass of the electron, is the charge of an electron, and V is the applied potential difference. From this equation, lambda proportional to the 1 upon under root of applied potential. Applied potential. Clear? Therefore, lambda 1 upon lambda 2 is equal to under root of V2 upon V1. V2 is given the 100 divided by 25. Therefore, root 4 is equal to 2. Therefore, lambda 2 is equal to lambda 1 by 2. Therefore, the de Broglie wavelength is decreased by 2. Decreased by 2 times. Again, here in electron microscope, the electrons are accelerated by applying the potential difference of 25 kilovolt. As we increase this potential difference to 100 kilovolt, what should be the de Broglie wavelength? So we know the equation of the de Broglie wavelength, lambda is equal to H upon under root of 2 MeV. H, M and E and also 2 are constant. Therefore, wavelength is inversely proportional to the square root of potential difference applied. So from this equation, lambda 1 upon lambda 2 is equal to V2 upon V1. So this ratio we obtain the 2. Therefore, new wavelength lambda 2 is equal to lambda 1 by 2. That is the decrease by 2 times. Now next, 35. Threshold frequency for photosensitive surface is given, F0 is given 8.3, 3.3 into 10 is to 14 Hertz. Now, the radiation of frequency F is equal to 8.2 into 10 is to 14 Hertz is incident on a surface. So what should be the value of stopping potential for given metal? Now we know that the kinetic energy K is equal to HF minus HF0 is equal to EV0. That is the Einstein's equation. Maximum kinetic energy is equal to HF minus phi or the HF minus HF0 is equal to EV0. Require the V0. Therefore, V0 is equal to, is common from these two, H upon E, F minus F0. Now we substitute the value. H is the Planck's constant 6.62 into 10 is to minus 34. Charge of electron 1.6, 10 is to minus 19 into bracket, F is given 8.2 minus 3.3 into 10 is to 14 common. So hence we obtain the answer is 2 volt. That is the stopping potential is required. Again, the threshold frequency for photosensitive surface is given 3.3 into 10 is to 14 Hertz. When the radiation of 8.2 into 10 is to 14 Hertz frequency is incident on it, what should be the value of stopping potential? So we know that from the Einstein's equation, maximum kinetic energy is equal to HF minus phi. Phi is the stopping work function. Value of phi is equal to HF0 is equal to EV0. We are using this concept. Therefore, V0 is equal to E is taken on left hand side in denominator. H is common from the numerator. Therefore, H upon E into F minus F0. Value of Planck's constant we know 6.62 into 10 is to minus 34 divided by the charge of an electron 1.6 into 10 is to minus 19. Now, into bracket the difference of the frequency and also threshold frequency. So we obtain the answer is 2 volt. Clear it? Okay. Now friends, the next numerical is asked in 2013. For photoelectric emission from a metal, cutoff frequency is given, that is F. If the radiation of frequency 2F is incident on a metal, right, the maximum possible velocity of emitted electron will be. Now for a given metal, the cutoff frequency is F is given, that means the threshold frequency is given. Now the radiation with the double frequency is incident on a metal. So what is the maximum possible velocity of photoelectrons emitted? For that purpose, we know that the maximum kinetic energy according to the Einstein's equation, half m square maximum is equal to HF minus HF0. Right? We are using this concept. Therefore, maximum kinetic energy half m v square maximum is equal to HF minus HF0. F0 is given F. Threshold frequency is F. Now, value of F is 2F. Now the radiation of double frequency is incident on a metal. Therefore, F has the value is 2F and F0 is F. Therefore, we substitute here as 2F minus HF is equal to HF. Therefore, V square maximum is equal to HF to HF upon M. Therefore, maximum speed of photoelectrons V maximum is equal to under root of 2HF upon m. Again, friends, for a metal, the cutoff frequency is given f, that means the value of threshold frequency is given. If the radiation of double frequency, that means the 2f is incident on a metallic surface. So photoelectrons are emitted because the frequency of incident radiation is more than the cutoff or the threshold frequency. So what should be the maximum kinetic energy or the maximum possible velocity of photoelectrons emitted? So from Einstein's equation, half m square maximum is equal to hf minus hf0. F is given to f and cutoff frequency or the threshold frequency is given f. We substitute here the value. Therefore h into bracket 2f minus hf. This subtraction is hf. So from this equation, v square maximum is equal to 2hf upon m. We require the maximum velocity. Therefore Vmax is equal to under root of 2hf upon m. 2hf upon m. Okay. After that, the next numerical or the next objective question asked in 2013. The wavelength lambda E for an electron and lambda P of a photon of the same energy. So what is the relation between their wavelength? Lambda is equal to what? So the lambda P is related with the wavelength of electron in which order or the which manner. For that purpose, we know that the de Broglie wavelength for electron, wavelength of electron, that is the lambda E is equal to h upon under root of 2me. Capital E is the energy of this electron or the photon, both having the same energy. Therefore, making the square, lambda E square is equal to h square upon 2me. So from this equation, energy E is equal to h square upon 2m lambda E square. 2m lambda E square. Now, wavelength of photon. Wavelength of proton. Lambda P is equal to h upon E. Is equal to h upon E. hc upon E. Therefore, hc upon value of E, h square into 2m lambda E square. 1 times h is cancelled. Therefore, 2mc upon h into lambda E square. That is the lambda. But here, 2mc upon h. H is the Planck's constant. C is the velocity of light. M is the mass of any proton are constant. Therefore, lambda P proportional to the lambda E square. There is the relation between the wavelength of proton and wavelength of an electron. Again, now listen here. It is quite complicated because the electron and proton are given having the same energy. Now listen. The wavelength of electron is lambda E and wavelength of proton is lambda P. What is the relation between these two wavelengths? So we know that de Broglie wavelength for electron having the energy is E. Lambda E is equal to h upon under root of 2me. Therefore, making the square, lambda E square is equal to h square upon 2me. Therefore, the energy of electron E is equal to h square upon 2m lambda E square. Energy is in terms of wavelength of electron. Now, wavelength of proton, lambda P is equal to hc upon E. Right? Sorry, wavelength of photon. from the characteristic of photon, the wavelength of photon is hc upon E. E is the value is this, therefore hc upon E is square upon 2m lambda is square. So 2mc upon h into lambda is square. 2mc upon h is constant, therefore wavelength of photon is directly proportional to the square of wavelength of an electron. So our first option is right. First option is right. Okay. After that, the next question is, when the energy of incident radiation is increased by 20%, the kinetic energy of photoelectrons emitted from a metal is increased from 0.5 electron volt to 0.8 electron volt. The work function of the metal is what? Again, when the energy of incident radiation is increased by 20%, the kinetic energy of the photoelectrons emitted from the metal surface is increased by 0.5 electron volt to 0.8 electron volt. What is the work function of a given metal? For that purpose, we are using the equation, Einstein's equation, half m square maximum for the kinetic energy is equal to hf minus phi. hf minus phi. When the kinetic energy is given, the 0.5 electron volt. At that time, the hf is the energy. hf is the energy of incident radiation. Therefore, hf minus phi. And when the final kinetic energy is 0.8 electron volt, at that time, the energy of the incident radiation is increased by 20%. Increased by 20%, that means the 1.2. 1.2. Therefore, 1.2 hf minus phi. That is our equation 1, that is our equation 2. We require the work function phi. Therefore, we have to multiply the equation 1 by 1.2 and then subtract from 2. Multiply equation 1 by 1.2 and subtract from 2. Therefore, our equation becomes equation 2 as it is 0.8 electron volt is equal to 1.2 hf minus phi. That is our second equation. Now we multiply equation 1 by 1.2. So 1.2 multiply with 0.5, so it becomes a 0.6 electron volt. Is equal to 1.2 hf minus 1.2. Now 0.8 minus, now listen, there is the minus, and minus plus. Therefore 0.2 electron volt is equal to 0.2 phi. Therefore phi is equal to 1 electron volt. That is the answer. Now again, friends, that is asked in 2014, when the energy of the incident radiation is increased by 20%, the kinetic energy of the photoelectrons emitted from the metal surface is increased from 0.5 electron volt to the 0.8 electron volt. What is the work function for this method? So from Einstein's equation, maximum kinetic energy is equal to hf minus phi. Now, initial kinetic energy is 0.5 electron volt, at the time the incident energy is hf. Therefore, 0.5 electron volt is equal to hf minus phi. Now, incident energy is increased by 20%, therefore hf is increased by 20%, therefore 1.2 hf. In this condition, the maximum kinetic energy is 0.8 electron volt. Therefore, 0.8 electron volt is equal to 1.2 hf minus 5. We require the work function phi. Therefore, equation 1 multiplying by 1.2 and subtract from 2. So first we have done this equation 2. 0.8 eV is equal to 1.2 hf minus 5. Now, equation 1 is multiplied with 1.2. Therefore, 1.2 into 0.5 is equal to 0.6 volt. Electron volt is equal to 1.2 hf minus 1.25. We are making the subtraction of these two equations. Therefore, minus, here minus, 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 plus. Therefore, 0.2 electron volt is equal to 0.25. Therefore, work function phi is equal to 1 electron volt. Clear? Okay. Now the next is also asked in 2015. A certain metallic surface is illuminated with monochromatic light of wavelength lambda. The stopping potential for photoelectric current is 3 electron volt. Now, if the same surface is illuminated with light of wavelength 2 lambda, that means the wavelength of incident light is next double. The stopping potential is V0. The threshold wavelength for this surface is, what should be the threshold wavelength? So again, the same equation, Einstein's equation, maximum kinetic energy is equal to hf minus phi is equal to EV0. Therefore, we can add EV0 is equal to hf minus phi. Therefore, EV0 is equal to hc upon lambda minus hc upon lambda 0. Therefore, stopping potential V0 is equal to hc upon E lambda minus hc upon E lambda 0. So, that is our equation of stopping potential. We require the threshold wavelength. Threshold wavelength, right? Lambda 0 required. Therefore, when the stopping potential is 3V0, at that time, the incident wavelength is lambda. Therefore, hc upon E lambda minus hc upon E lambda 0. That is our equation 1. And when the stopping potential is V0, at that time the incident wavelength is 2 lambda. Therefore, V0 is equal to hc upon 2 lambda minus hc upon E lambda 0. E lambda 0. Clear? Now listen, we have to find out the wavelength in terms of the lambda. Right? Threshold wavelength is this. That's our equation. Now equation 2 is multiplied by 3 and subtract from 1. Multiply equation 2 by 3 and subtract from 1. So one equation is this, 3V0 is equal to hc upon E lambda minus hc upon E lambda 0. Now there is multiply with 3. There is multiply with 3. Therefore, 3V0 is equal to 3hc upon E lambda minus 3hc upon E lambda 0. There is minus, minus, there is plus. So there is cancel. So as we simplify, so we obtain the 2 upon lambda 0 is equal to 1 upon 2 lambda. Therefore, lambda 0 is equal to 4 lambda. That is the value of threshold wavelength. Again, we are using the equation, Einstein's equation, EV0 is equal to HF minus phi. Frequency is not required here, we require the wavelength. Therefore, EV0 is equal to HF minus phi. Therefore, EV0 is equal to HC upon lambda minus HC upon lambda 0. And we substitute the value of the stopping potential. When the stopping potential is 3V0, at that time the wavelength is lambda. Therefore, 3V0 is equal to HC upon E lambda minus HC upon E lambda 0. When the stopping potential is V0, at that time the incident wavelength is 2 lambda. Therefore, equation 2 we obtain. Now we simplify these two equations. We obtain the threshold wavelength lambda 0 is equal to 4 lambda. After that, the light of wavelength 400 nanometer is incident on a metal with wave function 2.2 electron volt. The de Broglie wavelength of electron is what? For that purpose, the E is equal to HF is equal to HC upon lambda E. HC upon lambda E into in electron volt. In E. So as we substitute the value, we obtain the energy is 2.48 electron volt. S is the Planck's constant, C is the velocity of light, lambda is given, right, 400 nanometer, E is the charge of an electron, therefore we obtain the energy in terms of electron volt. Now, the maximum kinetic energy, K maximum, is equal to E minus R. Wave function is given 2.2 electron volt, therefore 2.28 minus 2.2. So we obtain 0.28 electron volt. That is the maximum kinetic energy, K maximum for the E. Now, de Broglie wavelength for electron, lambda is equal to H upon under root of 2me. If we substitute the value 6.62 into 10 is to minus 34 upon under root of 2, mass of an electron 9.1, 10 is to minus 31 into 0.28 into 1.6 into 10 is to minus 19. That is inside the under root. So we obtain the wavelength is equal to 2.8 into 10 is to minus 10 meter, approximate value. Therefore, the wavelength of the electron is either greater than or is equal to 2.8 into 10 is to minus 9 meter. Clear?